we present CUPID, Curating Data Your Robot Loves with Influence Functions. Consider the imitation learning setting, where a behavior cloning policy is trained on a diverse dataset of demonstrations to solve a task. When the policy is evaluated on the robot, however, it performs worse than expected. You might think that curating your dataset and training on only the best demonstrations will result in a better policy. However, doing so is extremely challenging because neither the properties of a demonstration nor its effect on training or validation metrics will tell you whether it contributes positively to your policy's closed-loop performance. We introduce CUPID, a method that curates demonstrations based on their downstream impact on policy performance. After training a BC policy, CUPID starts by estimating the policy's expected return from a set of closed-loop rollouts. Next, given any demonstration, such as one from the training set or a newly collected set, CUPID assigns a score to the demo based on its estimated causal influence on the policy's expected return. Finally, CUPID ranks demonstrations based on their performance influence and selects the top K, resulting in a dataset that most strongly contributes to policy success. Beyond simulated experiments, we conduct extensive experiments on hardware with state-of-the-art policy architectures, such as the diffusion policy. We consider 3 manipulation tasks, each representing a distinct setting where data curation may benefit policy performance. The Figure 8 task studies curation of mixed quality datasets, where training on lower quality demonstrations may degrade policy performance, as shown in this policy rollout. The Tuckbox task studies datasets with multiple solution strategies, where curation aims to promote strategies more robust to test time distribution shifts. For example, changes in the box's mass distribution may render the sliding strategy unreliable. Finally, the Bookshelf task studies curation of datasets that contain spurious correlations between demonstrated behaviors and task-irrelevant features. This may cause a policy to execute a failing strategy at test time based on the presence of a task-irrelevant feature, for example, the white background. We argue that an effective data curation algorithm should remain performant across all settings considered, rather than just one. On the Figure 8 task, both CUPID and a quality-seeking baseline, DEMINF, identify higher quality demonstrations during curation, which results in a more performant policy. In contrast, the random choice baseline produces a dataset with mixed quality demonstrations, leading to a less successful policy. On the Tuckbox task, CUPID correctly attributes observed policy failures at test time to sliding-only demonstrations, resulting in a policy that prefers the more reliable pick-and-place strategy. In contrast, the quality-seeking baseline mistakenly removes the less smooth pick-and-place demos, reinforcing the unreliable sliding behavior at test time. Random choice yields negligible performance gains. On the Bookshelf task, CUPID correctly identifies the spuriously correlated demos that drive failure, in this case horizontal pulling motion with a white background, and rebalances the dataset to mitigate their effect. In contrast, the quality baseline prioritizes the smoother horizontal pulling demos, which further reinforces the spurious correlation. Once again, random choice results in negligible performance gains.